Let's see what happens. Okay, welcome to Friday. So here we are, just to get used to looking at the syllabus. We're Friday, August 31st. There's a few problems. There's a couple of star problems. Those star problems will be due with the other star problems on Monday in class. In addition, there is a new web work that is probably open right now, although I would encourage you to watch me and not try to do that at the moment. And there are also the supplemental videos that I mentioned earlier. So my big goal today is to talk about sections 12.3 and 12.4, which introduce the dot product and the cross product, two things that you can do with vectors that have all sorts of kind of interesting geometric and algebraic implications. But that said, before I get going on that, are there any questions about the homework that you're working on right now that you'd like me to maybe give hints about? Yeah, go ahead.
The second star problem deals with like a 36 to 90 triangle. Is that right?
What number? Do you remember?
It's that one, number 13. And
got it. Okay. So, yeah, go ahead. What's your question?
The one with the vector corresponding, if you remove the vector corresponding to 4 o'clock, I had a hard time figuring out where that vector was points. I mean, I get that since we moved 4 o'clock, we're left with 10 o'clock, right? And then, do you visualize that with the 36 to 90 triangle?
Well, let's have a look at it here. So let me get my hands on a circle here, and let's see. So you've got some important places on the circle. You've got the cardinal points, but then you've also got these intermediate points, and they're all separated by what, 30 degrees? Okay. And as you've probably already noticed, when you have vectors from, from the center out, they all cancel each other. Okay. So if you remove the 4 o'clock vector, which is this guy, then what you're left with is the guy that's antipodal, this guy. Right? Okay. How do you find the coordinates of that vector?
It's like unit circles.
Right, so what angle is that in radians? It says pi over 6, pi over 3, pi over 2, 2 pi over 3, 5 pi over 6, excuse my handwriting. Excuse my handwriting again. All you need is the cosine of that angle and the sine of that angle. Does that answer your question?
Yep.
Okay. I think a more interesting question is the second part of this problem. What if instead all of the vectors have their tails at noon and their heads on the remaining digits? Before I go on, let me first note here that there's a typo in the back of the book with this answer. What is this, 12.2? I've already lost my place here. 13, thank you. This is, and thanks to Ryan for pointing this out, this guy here, the coordinates are switched. So the correct answer is 0, and in fact, the picture that I'm about to draw, the correct answer is 0, negative 10r. Okay? What you're really shooting for is that 10r. If you can convince me that it's 10r, that 10r belongs in this picture, the rest is really just how you chose to orient your coordinate system. Okay, so, but I think the natural way to orient the coordinate system is, this is the positive y direction, and this is the positive x direction. And in that situation, then the correct answer is 0, negative 10r. What's r? The radius of the clock.
If you want to use the radius equal to 1, that's fine with me. Unit circle. You can just say your clock is, 1 unit in clock units or something like that. Okay. Let's talk about this. So I'm not going to draw all the vectors in, but we've got a bunch of vectors that do something like this. There's a lot of symmetry here. The goal is to add up all of the vectors from here out to the corresponding places on the dial, including this vertical one. Symmetry helps you here a bit. What kind of help does symmetry provide when calculating this sum? Say again, Andy, louder.
All the x directions cancel.
All the x directions cancel, or the horizontal directions, perhaps, if you want to use a different coordinate system. So yeah, the horizontal component of this vector is equal and opposite of the horizontal component of that vector. So that's simplified your life significantly. Now it remains to figure out what the vertical components of all these vectors are, and then what? What do you do with those vertical components? You just add them all up. Okay, my last hint is you know quite a lot about these vectors. In fact, you know where the tips of all these vectors are. Let's just focus on this one vector right out here. What are the x and y coordinates of the tip of that vector? Remember your unit circle. Well, the angle's pi over 6.
Right.
Yep.
Cosine 5 or 6.
Right. Root 3 over 2, 1/2. And that's me assuming that the radius is 1. Root 3 over 2, 1/2. And presumably you can go all the way around the face of the clock and you can put those coordinates in. And if you can't, it's a good review exercise. That's enough information for you to figure out these distances.
For that further question, do you still assume that the floor is removed?
For that last part where all of them are, no, I want you to assume that all of the vectors are present.
Oh.
Yeah. Any other questions? Yes?
So real quick back when I wanted it and I had them all up, but then I did it multiple times, multiple ways, and I got 12, So, just show the extra tools.
Well, to be honest, I can't vouch for the 10. I haven't done the exercise. So,
Well, in the question, are you counting the vector that goes straight down? Because that would account for 2r. The vector.
I would be counting that, yes.
Yeah.
Let me read the problem. Where's my back button? There it is. What if instead all vectors have their tails at 12 o'clock and their heads on the remaining digits? To me, that's 1 through 11. So just turn it in, write it up, turn it in, and if your process is good, you'll get most of the credit. Okay, other questions?
I have a question on that.
Sure, go ahead.
On 12.111, that's the other starting point. I don't quite know what it means by describe intersection geometrically. Like,
You know
how
what?
do you picture?
Let's talk about, do you remember what it means for a point to be on the YZ plane? How can I just look at a point and say, oh, that's on the YZ plane? Right. Okay. So when you look at number 11, you're talking about a point that is on the sphere and also on the YZ plane. So if it's on the sphere, it satisfies the equation that presumably you were able to derive. And if it's on the YZ plane, what additional constraint can you apply?
Zero.
Yeah.
And then that should turn into the equation of a circle that you can identify. Does that answer your question? Okay. I mean, that describes it, right? It's a circle of radius whatever, centered at whatever.
Right.
That's a complete description.
Oh,
Okay. And what was the problem? That was the question.
huh?
You said you had a question and a problem?
No, that was the question.
Got it. Okay. Anybody else? Okay, I remind you I have office hours at 8 o'clock on Sunday night. So if you're working over the weekend and you get stuck on something, come visit me then. I don't give answers, but I'll give hints. Did you have a question?
I mean, I didn't know if you guys, it should be 12, not 10.
Should it be
If you're
12?
counting- If you're counting the vertical one?
Yeah, I am. Okay. So thank you for that. And I'll do the exercise when I get back to my office, and I'll let you know if it should be 10 or 12. But if you say it's 12, I'll take your word for it. So the answer in the back of the book is just wrong on many counts. Okay. That said, I did do enough of the exercise to know that it works out really nicely. There's a lot of cancellation, and it works out in a way that's really nice. You're not going to get crazy answers, and you know it's not going to be algebraically terrible. You're not going to have to add a lot of fractions and things like that. There's a ton of cancellation, even in the y direction.
If you think about it, if it's a circle and it's symmetric, like radially symmetric, then this, like to 1 o'clock and to, from 6 o'clock to 5 and 7 should be the same distance.
Yep. Yeah, there's a ton of symmetry even in the vertical direction. Write it out, play around with the coordinates, and you'll do fine. Okay, let's get on with today. What I want to talk about today, and my goal is to just kind of talk about the dot product and the cross product, and then hopefully come back and do some examples of both at the end. So we're building up, we've decided by enrolling in this class, you've decided to study calculus of vectors, the calculus of vectors. That's what we're doing. Before you can do calculus, you have to understand vectors. And that's what we're doing in this chapter. We're building up the machinery to understand and work with vectors. You have to do that. That's prerequisite information before you can start doing calculus. So we talked last time about addition, subtraction, scalar multiplication, etc. for vectors. Now we want to talk about two operations that are peculiar to vectors alone. There's not really any analog to the dot product and the cross product in real numbers. These are special to vectors. So let's talk about that. The dot product. This takes two vectors, and we usually use a dot to indicate the dot product. And it spits out a number, also known as a scalar. And boy, it just has the silliest implementation. Like, you could get a second grader to make this up. So let's say I have two vectors, a1, a2, a3, b1, b2, b3, and I want to dot them. I want to compute their dot product. I just multiply the coordinates and add a1, b1 plus a2, b2 plus a3, b3. Well, great. You know, why didn't I just, why did I do a1, b3, a3, b1, a2, b2, right? Why did I choose this particular thing to do to these two vectors? Turns out, as simple as it is, it turns out to be an incredibly useful thing to do to vectors because it carries a lot of information in it. And it's surprising to me, it still surprises me, that this actually has any use whatsoever. So this is a thing that we're going to choose to do to vectors. Let me show you how this thing becomes useful. I'm going to ask you to recall the law of cosines. It's okay if it's not right on the tip of your brain. Law of cosines. It talks. It's a relationship between the angles and the side lengths of a generic rectangle. And let me try to choose my letters carefully here. I give up. I'm going to just choose them. A, B, B, and C. That's a capital C. C. So I have this triangle, 3 angles, A, B, C, and 3 sides, little a, little b, little c. And the lowercase letter is opposite its uppercase angle. Got it? Okay. With that configuration, the law of cosine says that c squared is equal to a squared plus b squared, which looks a lot like the Pythagorean theorem, minus 2ab cosine. And let me make sure I get the right angle here. C.
And that doesn't need to be a right triangle, right?
It does not need to be a right triangle. So this is a generalization of the Pythagorean theorem. Right? If you make this a right triangle, then the angle C becomes pi over 2. Cosine of pi over 2 is 0, and you get c squared equals a squared plus b squared. So it's a generalization of the Pythagorean theorem. Okay, well, how does this bear on the dot product? Let's make a triangle out of a pair of vectors. We can do that. And let's indicate the angle between these 2 vectors. Now, I know what you're thinking. You're thinking, well, these are vectors in 3 dimensions, so they're like this. And I'm drawing them on the plane, but it's okay, because I can always take a couple of vectors like this and get them into a plane. I can just lay them down. So I haven't really lost any generality. A and B are 3-dimensional vectors, and I've decided to consider them in the plane that they lie in. Okay. The third side, if I draw it in this way with the tail here and the head here, how can I write the third side in terms of the first 2 sides? A minus B. Good for you. So if the tail is up here at B and the head is down here at A, then that's A minus B, right? Okay. What's the length of this side? Magnitude of A. And similarly, the length of this side is the magnitude of B, and the length of this side is the magnitude of A minus B. Right? There's a difference between the vector and the length of the side, which is the magnitude of the vector. But you can see possibly now where we're headed with this. We're going to take the angle theta and these 3 magnitudes, and what are we going to do with them? Shove them into the law of cosines. Playing the role of capital C here is theta. Playing the role of little c is the magnitude of A minus B, and so on all the way around. Let's do that. So if I've made my substitutions correctly, that should be the expression. That's the law of cosines applied to this vector-based triangle. All right, let's play around with this a little bit. A minus B. How do you compute A minus B?
Find the magnitude of the vector resulting from A.
Well, not so much, I don't want the magnitude yet, just A minus B. I just subtract the components, right? Okay, so you're 1 step ahead of me. So what I really want is the magnitude of this vector. And on the right-hand side, there are similar things. I'm not going to write it out. I'll write out the first one, say. Oops. Yeah, I'll just write out. Okay. The magnitude of this guy squared, what does it look like?
The distance formula that's not under the bracket.
Exactly. The square wipes out the square root on the magnitude. And so what I'm left with is a fairly simple expression. A1 squared plus A2 squared plus A3 squared. Does everybody see that? I'm not going to write it out, but that's what we're looking at. I'm going to do some. We're going to do some algebra in our heads here for a little while. Similarly here, what's that? In terms of coordinates, what does it look like? B1 squared plus B2 squared plus B3 squared. Good. So there's a bunch of squared stuff here. How about this guy? Well, it's this squared plus this squared, right? Let's look at one of these guys. What happens when I square this out? Well, I get A1 squared plus B1 squared minus 2A1 B1, right? Now, there's an A1 squared here, and there's an A1 squared here. And they cancel, right? Because they're on opposite sides of the equation. And there's a B1 squared, and there's a B1 squared here. And they cancel. Again, because they're on opposite sides of the equation. And there's an A2 squared and a B2 squared. And an A3 squared and a B3 squared. So in the end, after all the cancellation, what happens to these two guys? They're gone. What's left behind on the left-hand side? What are those terms called? They're called cross terms, right? When you FOIL, all the cross terms are left. What do I mean by cross term? There's the A1 times B1, the A2 times B2, and the A3 times B3. But how many of them are there? There's a -2 on this one, a -2 on this one, and a -2 on this one, right? Okay, so I'm just ready to start writing again. On the left-hand side, we have -2 times A1 B1 plus A2 B2 plus A3 B3. And on the right-hand side, what's left? Yeah? What are you itching to do right now? Cancel the 2. And what's another way of writing this thing? A dot B. That's the cosine identity for the dot product. It says that the dot product is equal to the magnitude of A times the magnitude of B times the cosine of the angle between the two. So this is really interesting. This number, this crazy number that you get just by multiplying coordinates together and adding them, is somehow related to the angle between the two vectors. That's just bizarre. I mean, I see the proof and it's just still bizarre to me why that should be so, but it is. This leads us to, so this is a nice algebraic result, and this leads us to a nice geometric result. A really nice geometric conclusion that says A dot B equals 0 if and only if A is perpendicular to B. If A is perpendicular to B, what's the angle between them? Pi over 2. What's the cosine of pi over 2? That's where that comes from. So we have this really quick and simple measure to tell us whether two vectors in three-dimensional space are perpendicular. And we'll come back to this and we'll see it in action, but this is why the dot product is interesting to us. Well, one of the reasons why. Okay. How many of you guys have had physics? It's not important if you have or you haven't, just, okay. So those of you that have had physics, you know that vector quantities can be decomposed into, say, things like this. So if I have a vector here, I can decompose it into, say, a horizontal component and a vertical component. Ring a bell a little bit, anyway? Okay. The dot product makes that really easy as well. And let's see how that works. So here's one big idea about the dot product, this geometric result about perpendicularness. Another big result is what we call projection. So the projection of one vector onto another. So a really common thing to want to do in physics is perhaps to have a vector. Let me draw it in red here. And let me get another vector. Okay, let's call this first one, let's call the second one B, let's call the first one A. A really common thing to want to do is to try to figure out the piece of A that lies in the direction of B. So this is a generalization of the thing that I was just telling you about in physics, where you want to find, say, the horizontal component and the vertical component of a force or of a velocity. So here I have a direction B that I'm really interested in, that's really important to my problem. And I have this force A, or this velocity A, and I would like to know how much of that force or how much of that velocity lies in the direction B. That's called the projection. That's the projection of A onto B. We can use the dot product to very quickly find this projection. So let's go through that. All right, I'm going to sketch in the angle because it's useful. It turns out that we won't need it in the end, but it's useful for intermediate calculations. So we have this vector A that we're trying to decompose or project onto B. And we know that it makes an angle theta with B. What I would like to do is build the vector, build that blue vector. What direction does that vector point in? It's the same direction as B, right? So we know we're already ahead of the game. We've got half of the thing, right? What's a vector? It's a magnitude and a direction. So we've got the direction down. We know which direction the thing's supposed to go in. What's the tough thing? The magnitude. Can we figure out the magnitude of this blue vector? Ideas?
We have a formula for that.
A cosine theta, anybody? Magnitude of A times cosine of theta? Yeah? Great, so we have the magnitude and we have the direction. Can you build me a vector? Can you build me the blue vector with this information?
Where is A cosine theta?
So this is a right triangle, and maybe I didn't make that clear, but let me put a little right angle in there. Okay?
Oh.
And now all the trig stuff comes into play. Yeah, I should have put that in there and I forgot. Yeah, because what we're trying to do is this right angle situation. Okay. What's the magnitude of the projection? We've got that. What's the direction of the projection? We've got that. Can we put these two guys together and build ourselves an honest-to-goodness vector that represents the blue guy? Sorry?
We don't have cosine theta.
Exactly. We don't really know theta. Let's keep working here. As an aside here, I'm going to try to find an exercise in the book here. Anybody do 11 yet? Let P be 4, 5, 6. Let Q be 1, 2, negative 5. Find PQ. How do you find PQ? Subtract them, right? Okay, so that we all know. How do you find a vector in the same direction as PQ but with length 1? Divide it by its magnitude, right? That creates a unit vector, right? That's described in the section. So you take the original vector and you divide by its length, and now you have a vector of length 1 that points in the same direction. Let's do the last one. How do you get a vector that's in the same direction but has length 4? Take the unit vector and do what? Which scalar? 4. Yeah. So what we see here in problem 11 is precisely what we need to do here. I know the magnitude, I know the direction. Now I want to build a vector in the direction of B with length, magnitude of A, cosine theta, with noting that we still do have to get rid of the theta, but we're going to do that later. Okay, so let's go through the steps from that exercise. Let's build a unit vector. How do we build a unit vector in the direction of B? So B over the magnitude of B. Like that. And then how do I get its magnitude to be the length of A cosine theta? I just multiply by that scalar, right? This is the blue vector. This is what we seek. But there's this little issue of the theta. Can we get rid of the theta and express this thing in terms of stuff that we know? We don't really know theta. We know A and B.
Cosine has A or theta in it? Cosine theta.
This dot product identity, which appears to have been slightly truncated. This dot product identity should do the job for us. So let's go down here and look at what we have. We've got A dot B, magnitude of A, magnitude of B, cosine of theta. And we have A cosine theta here, so we know that the A cosine theta is equal to what? It's equal to that. And now we can go ahead, and this is just a little aside here. Now we can go ahead and rewrite this guy as A dot B over the magnitude of B times B over the magnitude of B. That's the projection in terms of the two vectors, which is all the information that we have. Let me step back here a little bit and talk about some notation. This dot and this dot, are they the same dots or different dots? They're different dots. The first dot, second dot, multiplication. You have to figure out what the dots mean from context. What do I mean by that? Well, this thing here is a scalar, right? And this is a vector. It's impossible to dot product a scalar with a vector. Therefore, that dot must be scalar multiplication. This happens all the time in mathematics because, sadly, there are a finite number of symbols to use in the world, and often those symbols carry the burden of multiple meanings, and you have to figure out their meaning from context.
That's the projection.
And we can clean this up a wee bit. We can write this as A dot B over the length of B squared times B. And again, there's still that dot product dot and that scalar multiplication dot. Let me do this with a very straightforward example that'll hopefully bring this home to you. What, you're not writing for me now? There we go. Okay, and let's try to keep our colors consistent here. Let's go with this guy. And let's call that 5, 3. And let's go and call this X and call this Y. And what I'd like to do is get my hands on that vector and maybe even this vector. Bless you. Okay.
This is a pretty straightforward situation, and you don't really need dot products to do this, but I want to try to make the point. This vector, the original vector, the component of the vector in the x direction is really the projection of this guy onto this guy. So we can use this formula.
Let's let this be our vector A.
We need a vector in the horizontal direction. Do you have one in mind? If I want to find this blue vector, I need to find a vector that points in that same direction so that I can use the projection formula. 1, 0 is a perfectly fine example of that. 1, 0 is, say, here, and it points in that direction. I'm going to ask for another example because 1, 0 is going to not quite make the point that I want to make.
0?
Sorry?
5, 0?
5, 0? 10, 0, somebody said? Yeah. Let's try one of those slightly more inefficient, I think is probably the word, vectors. So we'll choose B to be, what did we decide, 5, 0? So what I want to do is find the projection of A onto B. We know the answer. What's the answer? 5, 0, right? It's the vector 5, 0. And if we were to do this in the vertical direction, we know that answer too, right? 0, 3. So this is really just a confirmation exercise. So I have this original vector A, and I have this vector B that points in the direction upon which I'd like to project. Let's just apply the formula. What all do we need? We need A dot B, and we need the length of B. So let's calculate those two things. A dot B. What is A dot B? $25, exactly. It's 5 times 5 plus 3 times 0. Make sense? Multiply the first coordinates, multiply the second coordinates, add them together. Okay. What is the length of B? Or better yet, what's the length of B squared? 25. So that's 5 times 5 plus 0 times 0, 25. Okay. Let's keep going here. Let's fill in A dot B over B squared times B. Let's see. A dot B over B squared is 1. And B is 5, 0, and that is the projection. The point, and the reason I didn't want to go with 1, in fact, I probably shouldn't have gone with 5 either, but that's okay. This will work with any
vector B that points in the proper direction. So we could use 10, 0, or 100, 0, or 1,000, 0, or a 1, 0. And this projection will return to you 5, 0. Always going to be the same. Okay, and you could do the similar exercise in the vertical direction and you would get 0, 3. And it doesn't matter whether you use 0, 1, or 0, 10, or 0, 100. Okay, but the dot product provides a really quick way of doing this calculation. And in fact, let me show you some stuff at the end of the section here. There's some nice algebraic results at the end of the section here. For example, the first one here says that u dot u is the magnitude of u squared. You buy that? Think about u dotted with itself. That's u1 squared plus u2 squared plus u3 squared. If you took the square root of that, you'd have the magnitude. Since you don't have the square root, you have the square there. How about this guy too? U dot v equals v dot u. We have a word for that in mathematics. What does that say about the dot product as an operation? Close. Commutative, yes. It's a commutative operation. Commutative means I don't have to worry about the order. I can do u dot v or v dot u. How about 3? What mathematical property is that demonstrating? Yes, that says that the dot product distributes over vector addition. And the last one? That's actually one of the properties also that you run into in algebra. Sorry? Associative. It says that scalar multiplication is associative with dot product. Okay? So these are just some basic algebraic properties. I would encourage you not to forget about these guys because there'll be times in the coming weeks where you're going to have some vectors and you're going to be dotting them together and you're going to want to do a calculation. You're going to start digging into the coordinates and pushing coordinates around. And you'll notice that none of these identities talks about the coordinates of u or v. Sometimes you can escape algebraically unscathed by using some of these guys, not digging into the coordinates. I encourage you to only look at the coordinates as a last resort. If you can use these higher level identities, it can save you a lot of time and effort. Okay, so what I want to do is I want to draw your attention to this guy, and then let's go back to the scalar projection. This is really A dot B over B dot B dot B. Just sort of looks nicer that way. A dot B over B dot B times B. That's the projection onto B, the projection of A onto B. All right. Oh, I got plenty of time. Okay. I was getting a little nervous there. Let's go back and start talking about cross product, and then we'll come back and maybe do a few more examples. Okay, the cross product. This takes two vectors, and it produces another vector. That's an x. And this vector is perpendicular to both A and B. That's not a terribly difficult thing to imagine. Here's a vector, here's a vector. I put them together like this in 3 dimensions. Are there vectors that are perpendicular to both of these guys? Sure, they kind of point along in this direction, right? How many are there? There's a lot of them, yeah. There's an infinite number of them, right? Because you've got this one, and you got this one, and this one, and this one, and you got this one, and these guys down here, right? So if I take any two vectors, any two non-zero vectors, there's a whole bunch of vectors that are perpendicular to these guys simultaneously. One such vector is the vector that's produced by this guy, and I'll define it in a minute. Question?
In your in your demonstration, it pointed from the point of intersection. Is it always going to go there, or I mean, because any vector over here that point in the same direction as you bring it into, will the cross product give one here?
Right. Vectors don't have location. So when I say, you know, that it's a vector here, 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 or here, I'm using that for convenience. But that vector could be over here, right? Because remember, vectors are direction and magnitude, but not location. Okay. So in fact, when I talk about these two vectors, they don't need to be tail to tail. You know, one's here and one's over here, and then there's this guy over here that's perpendicular to both of them. So location is irrelevant, but it's convenient to put them tail to tail like this, and then think about that perpendicular vector here. But it's a good. You make a good point. These guys are location free. Okay. So A cross B produces another vector that's perpendicular to both A and B. I wish that this formula were as nice as the dot product, alas. Let me show you how to compute this thing. Let me reiterate what A and B are. So A is our friendly A1, A2, A3. B is going to be our B1, B2, B3, and here's a mnemonic that's described in the book, and it's one that I use to this day. Are everybody familiar with I hat, J hat, and K hat? Do you know what those guys are? Have you seen them before? It's okay if you haven't. I hat is this vector 1, 0, 0, which is used so often that we give it a special name. J hat is that guy, and K hat. These are called the standard unit normal vectors. And they point along the X, along the Y, and along the Z. I, J, and K. Why they have those names, I don't know. Okay. Here's my little mnemonic. I want to compute the cross product of A and B. Bless you. So, a word of warning here, the cross product is not commutative, so the order matters. So if I have A cross B, I put A on top and then B. And then my mnemonic works. How does it work? Cross out the first column, and then look at A2 times B3 minus A3 times B2. That's the first coordinate of the vector. To get the next coordinate, you block out the middle column, A1 B3 minus A3 B1. And there's a slight hitch. The middle column, for some strange reason, has its own minus sign.
Those supposed to be constant, not vector.
Right. And then this, to get the third coordinate, you blot out the third column, A1 B2 minus A2 B1. And it doesn't have its own minus sign, so you're back to the original A1 B2 minus A2 B1. And those three numbers together form the coordinates of the cross product. I know it leaves a lot to be desired as a mnemonic, but it's better, possibly better than memorizing this expression right here. It does have this convenient feature that it's perpendicular to both A and B. And that's why we care about it so much. I'll do a couple of cross products in a minute. What I'd like to do is derive an identity that is somewhat complementary to the cosine identity for the dot product, and that's the sine identity for cross product. And I'm going to have to get out my notes because I have to remind myself. Okay, so the sign identity for cross product, similar to the dot product identity, but definitely not the same. You start out by computing the magnitude of A cross B squared. And I would just stop there. No. Right, this is disgusting. Here's A cross B, and now you have to square this, and square this, and then add them all up. So, to save you the pain and misery, I'm going to skip a few steps and reveal the remarkable result that after all that pain and misery, if you group the terms in just the right way, it turns out to be the magnitude of A squared times the magnitude of B squared minus A dot B squared. Pretty remarkable. It's not that bad. I just feel like there are better uses of class time. So it's totally doable. Okay. So what have I done there?
The cross product.
Dot product identity?
Huh?
It's just the dot product identity, right? The law of cosines dot product identity. So I took A dot B and I replaced it with this guy. Everything else is the same. Okay. What did I do there? Yeah, I squared the stuff that was inside. I got A squared, B squared. Oh, but there's an A squared, B squared over here. Factor it out. 1 minus cosine squared. What's 1 minus cosine squared? Sine squared. Very good. And take the square root of both sides. The magnitude of the cross product, not the cross product, but the magnitude of the cross product is the magnitude of A times the magnitude of B times the sine of the angle between them. When I took the square root, why didn't I put absolute values around the sine of theta? When technically in algebra I probably should have done that. Is there a reason why I can ignore those absolute values?
Those are vectors.
No, not quite. Kind of. Can you elaborate? Or can anyone else elaborate? I want you to think about the geometry.
Yeah, you can put them anywhere.
Here are the vectors, right? And what's theta?
The angle is-
The angle between them. What's the range of theta?
360.
It's not quite 360, right? Because when I get to here and then I go past it, what happens?
Flipper.
I just start using the smaller angle because that's the angle between them. Okay? So what's the range of theta? Starting all the way up here, 0, all the way down to 180, pi over 2. Sorry, pi. What's the sine, S-I-G-N, of the sine, S-I-N-E, on that interval? Positive. So I can drop the absolute values. Okay. Okay. That is the sign identity for the cross product. This has geometric implications. What kind of geometric implications do you think this has? This has a nice test also. It tests something about the vectors. When is the cross product going to be 0? When the vectors are parallel. So this is kind of an exact complement to the dot product. When is the dot product 0? When they're perpendicular. When is the cross product 0? When they're parallel. So these are really complementary things. And they're complementary in another way that you just kind of have to drill into your head, and that is the dot product produces a scalar quantity and the cross product produces a vector quantity. Don't forget that. And so when I say that the cross product is 0, what I mean is the cross product is the vector 0, 0, 0. Or the magnitude of the cross product is 0. The only way for a vector to have magnitude 0 is if it's all zeros. Okay, so you have this nice dichotomy, this yin and yang kind of thing going on between the dot product and the cross product. If you think of it in that way, I think it'll help you remember the properties of each. Okay. Now, another interesting result about the cross product that we're not going to use for quite a while, probably around about the 10th or 11th week of the semester, what we'll be doing is building what we call surface integrals, where we'll have this nice surface sitting in space, and what we'd like to do perhaps is calculate, well, a really simple example would be to calculate the surface area of some surface floating in space. So what we're going to do is, just like in Calc 2, where we chopped up the interval into little pieces and we summed up those infinitesimal pieces, we're going to take the surface and chop it up into little pieces, infinitesimal pieces, and we're going to add up all these little infinitesimal surface areas. And those little infinitesimal surface areas in calculus, in Calc 2, we had little infinitesimal subintervals. And in Calc 3, when we do the surface integral, we're going to have little infinitesimal parallelograms. And the cross product is a really quick way of computing the area of a parallelogram. So let me talk about that. So you'll note this, and you'll say, yeah, that was interesting, and you'll forget it, and then in about 10 weeks, I'll bring it up again. So the area of a parallelogram, let me remind you what a parallelogram is. There's a parallelogram. Anybody know the area of a parallelogram? Base times height, good, very good. So let's draw the height in. Oops. H. And the base here, I'll put the base up here. And the area is base times height. Two vectors naturally form a parallelogram in the following way. If I take two vectors and I put them tail to tail, they naturally form this parallelogram. Does everybody see that? Okay. And again, we have to bring up the angle here. In terms of A, theta, and B, let's try to figure out what H and B are. Bless you. So H, in terms of A and theta. Right. B, little b. It's just the magnitude of B. Little b is the magnitude of big B. Okay, good. So we get the magnitude of A times the magnitude of B times the sine of theta, which is the magnitude of A cross B. So the area of a parallelogram is just the magnitude of the side vectors, A cross B. And we will use this, like I said, about 10th or 11th week. Okay. Let's do a few little, well, let's do one explicit example, and then we'll do a few little exercises. Let's do some cross-producting. How about just one of these straightforward ones, maybe two here. So let's find the cross product of 1, 0, 2 and -1, -2, 4. So whenever I'm going to cross product vectors, I always write them one on top of the other. This is the first one, this is the second one. And then I use my little mnemonic device. And so the cross product here, if I want to just put a little X in between them, I blot out the first column, and I do 0 times 4 minus 2 times -2, which works out to 4. The second column, remember the second column comes with its own minus sign. So we'll put that in there just so we don't forget. And then we have 1 times 4 minus 2 times -1. 6, good. Last one, we blot out the last column and we do 1 times -2 minus 0 times -1. -2. Okay, and simplifying this a little bit, we get 4, -6, -2. Now, what's a way to check and see at least this possibly is the correct answer? How geometrically should this vector be related to these two guys? They should be perpendicular. How can we test whether that guy is perpendicular to each of those other guys? The dot product. So if we take the dot product of this result with this vector, what should we get? Do we get 0? We sure do. 4 times 1 plus 0 times -6 plus 2 times -2. 4 minus 4, 0. How about the other vector? -4 plus 12 minus 8. Yep. It's perpendicular to both of these vectors. Doesn't necessarily mean that that's the cross product, but at least you found a vector that's perpendicular to both of them. It is the cross product. I mean, if you get that far and it's perpendicular to both of them, but it is a good way to check and catch an error. So if you compute a cross product and one of these guys fails to be 0, you know you have to go back and check your work. Okay, let's play around with IJK here in the waning minutes. Okay, so I've drawn a coordinate system. This is different from the coordinate system that I drew, oh gosh, I don't remember when that was, Wednesday. It's the only other class we had. This is different from the coordinate system that I drew on Wednesday because the positive y-axis is going into the board now instead of out of the board. So if you're looking at your notes and comparing the two, make sure that you pay attention to this. This is what we call a right-handed coordinate system. It's really the one that you should use in general, and not one that I used on Wednesday. Mostly, I don't know. In the case where it doesn't matter, I just don't bother. But okay, this is a right-handed coordinate system. I cross J. Let's do it the hard way. So I'm going to use my mnemonic, and I'm going to build I cross J. Let's do it really quickly. 0 times 0 minus 0 times 1. That's easy. Blot out the middle column. 1 times 0 minus 0 times 0. That's 0. And then finally, the last, blot out the last column. 1 times 1 minus 0 times 0 is 1. So that's K, right? That's K? Okay. How many of you have heard of the right-hand rule from physics? Okay, let's talk about the right-hand rule with respect to cross product. The way the right-hand rule works is you put your fingers along the first vector in the cross product and your palm facing the second vector. So I'm going to put my fingers along the direction of I, and my palm is facing the second vector, J. Where's my thumb pointing? That's the same direction that the cross product will point. Okay, let's switch it up. Let's try J cross I. Now I put my fingers along the direction of J, and remember my palm has to face I, so that forces me to turn my right hand over. What's J cross I? Minus K. And you can go all the way around the block here with this. Let's do something like K cross J. K cross J. Put your fingers towards along K and your palm towards J. What do you get? Negative I. And it doesn't just work with unit vectors, it works with any pair of vectors. You put your fingers along the first vector and your palm towards the second vector, and your thumb's going to point in the direction of the result. Doesn't give you the magnitude, but at least gives you the direction. That's the right-hand rule. Okay. Well, I think I'm done. Any questions? All right, have a good weekend. So hopefully this video thing worked, and I'll send you an email around about it if it did.